Another way of representing our probability events or experiments is through use of a tree diagram. Okay, so we often use a tree diagram to represent multi-stage events. All right. To be honest, there's normally only 2, maybe 3 possible outcomes, and we probably wouldn't have any more than 3 trials. Most of the time, 2 outcomes, it's either a win or a loss, and we often only do it once or twice, or 2 probably. All right. Otherwise, the tree diagram gets too big. So a couple of key features of our tree diagram. We use it for multi-stage experiments. We put the probabilities of each stage onto the tree diagram itself. The probability of the next stage happening depends upon what happened previously. So if I just come down to this tree diagram here, the probability of this second P here, and we'll talk about what that stands for, will depends on whether or not the previous P happened. Yeah, so the next stage in the event depends upon what happened in the previous event. All right, a couple of things to note. For my probabilities, any one set of branches, the probabilities have to add to 1. Okay, so if we look at each of the little pairings in there, each of those probabilities add to 1. So the 3/4, 1/4 there, 3/4, 1/4. So the first set of branches, that's trial 1. So that's the first experiment. The next set of branches, that's trial 2. If we had to try and fit another one in, obviously that's when it gets a bit messy. Let's look at it and have a look. Suppose the probability of a student owns an iPhone is 0.75. If 2 students are selected at random, construct a tree diagram and use it to determine. All right. First things I'll do, whenever I'm using a tech-free environment, I'll try to write my fractions or my decimals as a fraction. Because 0.75 by 0.75 is difficult to work out. But 3/4 times 3/4, well, that's just 9 on 16. So it's a bit easier to work out fractions when we're multiplying them with our calculator. So we either get a phone P or P dash, we don't get a phone. So it's often it's either a success or a failure. All right, so we might rather get a tail or not a tail. You might be a female or not a female. Even though we have names associated for not a female, and that's obviously male, we often put the dash. Okay, P and P dash. Probability of owning a phone is 3/4, which means the probability of not owning a phone is 1/4. And if I do that trial again, the probabilities don't change, right? Because our probability pool is the same. Probability that both students selected own a phone, that's just probability of P times P, own a phone. So we multiply across the branches, 3/4 by 3/4, which is 9/16. The probability that only one student owns a phone, well, you've got to think of all the ways only one student. If I select 2 of them, the first one might own a phone, but the second one won't. Or the second one will own a phone and the first one won't. So we get P times P dash, so P and P dash union P dash intersection P. So I've got an extra dash there. Let's get rid of that. Yeah, so only one of those events. So there's 2 ways one person can own a phone. So P intersection P dash, if we follow the branch along, P intersection P dash is that branch there, 3/4 by 1/4. Or we could go with P dash intersection P dash intersection P, 1/4 times 3/4. If we add them up, we'll get 3/8. Let's have another look. Suppose that in a certain town, the probability that it is sunny on Saturday is 3/8. Okay, and if it's sunny on Saturday, then the chances of it also sunny the next day is 5/8. If it's not sunny on Saturday, then the chance of it being sunny on the next day is only 1/4. So I've decided to write out the full word here, sunny. If I just put an S, you could get confused with is it Saturday or Sunday. If I just put sun for sunny, you could think it's Sunday. So I just wrote sunny. So I'm going to say it's either sunny or it's not sunny. All right. The chances of it being sunny on Saturday was 3/8. So we put our 3/8 in there for sunny on Saturday, which means the chance of it not being sunny is 5/8, because one of the two things must happen. Now, if it's sunny on Saturday, the chances of it being sunny again is 5/8. Okay, so that sunny branch there is 5/8. The chance of it not being sunny is 3/8. If it is not sunny on Saturday, the chance of being sunny on the next day is only 1/4. So this sunny outcome depends on the previous sunny, where it's not sunny. Yeah, not sunny on the Saturday, sunny on the Sunday. It's only 1/4 then, okay, which means it must be 3/4 of it not being sunny. So my questions would be, so the probability of it sunny on both is the probability of it being sunny, sunny. So if I follow the sunny, sunny branch, I get 3/8 times 5/8, which is 15 on 64. All right. The probability of it being sunny on Sunday, well, it could be sunny, 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 or it could be not sunny, then sunny, not sunny, then sunny. Sunny, sunny, we've worked out already. That's my 15 on 64. Now, not sunny, then sunny. Not sunny is this branch here. 5/8 by 1/4, which is our problem there. When we have an or, it's sunny, sunny, or not sunny, sunny. The or means we add. Yeah? So that's why we add those two terms together, and we'll end up with 25 on 64. Next page, I think. Yeah, there they are. The probability that it's sunny on both or just sunny on. Okay, our next little definition is we want to talk about is conditional probability. And conditional probability is an event, the probability of an event occurring given something else has happened. So if I said to you, what's the probability of rolling a 6-sided dice and getting the number 4? Well, obviously it's going to be 1 in 6. But what if I said to you, what's the probability of rolling a 6-sided dice and getting a number 4, given I rolled an even number? Now, the given I rolled an even number is a conditional probability part. I'm telling you I rolled an even number. So now, instead of having 6 possibilities, I've only got 3, a 2, a 4, or a 6. I told you that. And the chance of then rolling a 4, if I have rolled an even number, is going to be 1 in 3. So there's my conditional. That's an example of my conditional statement, okay? The notation for conditional probability is A\B, which is read as A given B. What's the probability of A happening given event B has happened? All right. And the rule for A given B is the intersection of the two over the probability of the second one. So the probability of A given B is A intersection B over the probability of B. The probability of B given A is different, is the probability of B intersection A over the probability of A. It's worth noting that the probability of A intersection B and the probability of B intersection A are the same thing, but it's the denominator that's different. So just a couple of, trivial examples. Given that for 2 events A and B, A is equal to, B is equal to, and B given A is equal to, fine. Probability of A intersection B. Well, since I've got B given A, I'm going to use the B given A form of the rule. So the probability of B given A is equal to the probability of B intersection A, which is the same as A intersection B, over the probability of A. So if I just substitute those values in, I can get the probability of B intersection A is 0.28, which is the same as A intersection B, so I've got what I was after. Next part, find A given B. So the probability of A given B is A intersection B over B. A intersection B, I've just worked it out, is 0.28 over 0.3. So 0.28 over 0.3, multiply top and bottom by 100. I get 28 over 30, which is the same as 14 on 15. All right. Multiple choice, 2 events, A is given, B is equal to, A intersection B is equal to, the probability of A given B. A given B is A intersection B over B. 3/10 over 1/3, divide by a fraction, flip it upside down and multiply. and we end up with 9/10, which is D. Okay. Let's have a look at a more practical sort of example. All right. In a certain town, the probability that rains on any Monday is 0.21. If it rains on the Monday, so let's have a look. Rains on the Monday. There's my 0.21 and 0.79. If it rains on Monday, then the probability that it rains on Tuesday is 0.83, which means it's 0.17 that it doesn't rain on Tuesday. If it doesn't rain on Monday, then the probability of rain on Tuesday is only 0.3. So down here to the bottom, if it doesn't rain on Monday, no rain, the chance of it then raining is 0.3, which means the probability of it doesn't raining is 0.7. So you notice how the probabilities in that second branch change depending upon what happened in the first branch. That's conditional upon what happened in the first branch or the first experiment. Probability of rain on both Monday and Tuesday is the probability of rain. So if I follow the rain path, let's just highlight that, rain path, 0.21 by 0.83 on a calculator, 0.1743. Okay. The probability of rain on Tuesday. Well, rain on Tuesday could be the rain path, which was already got, 0.1743, or we could have no rain, then rain, which is the 0.79 by 0.3, which on a CAS calculator is 0.237, I think that says. And if I add them up, I get 0.4133. All right, those sort of decimals you would expect to have a calculator for. Off you go.